All right, guys, so this video is picking up, continuing with salt hydrolysis from where we left off in class. So we previously just had a salt and did those hydrolysis reactions of looking at what would be produced from the salt itself. So here we have the example of ammonium with that OCl attached to the end. So if we were to split this, our individual ions are going to be the ammonium and the OCl. Now, one thing that we can look at to tell if it's acidic or basic is compare the Ka and Kb values. So if we were to write out a hydrolysis for both of these, so looking at ammonium and the OCl, and they both react in water. So ammonium is going to give up a hydrogen to produce the hydronium and NH3, which is ammonia, which is a weak base. So that means that this is acidic. But we need to check both ions. The OCl, because it's negative, attracts the hydrogen to produce HOCl and hydroxide. This produces a weak acid, so this is basic. So whenever neither ion cancels out, you have to compare Ka to Kb to see is the salt acidic or is it basic, whenever neither cancels out. So if your Ka and your Kb value of the two are equal, it is neutral. They're going to cancel each other out. If the Ka value is greater than the Kb value, it is going to be an acidic salt because the acid is going to be stronger. If the Ka is less than Kb, Kb is greater, therefore it is basic. And if this is the case, you will have Ka or Kb values given to you to reference to tell if it's acidic or basic. So here, looking at our numbers, the Ka for ammonium is 5.6 times 10 to the negative 10th. Now, it did not give us Kb, but it gave us Ka of the HOCl. So remember, we can find Kb because Ka times Kb equals Kw. So what we can do to change this into Kb is we can do 1.0 times 10 to the negative 14th, that Kw, divided by Ka, 3.5 times 10 to the negative 8th, and we get our Kb value, which is equal to 2.9 times 10 to the negative 7th. So when we're looking at this, Ka was 5.6 times 10 to the negative 10th. Kb is 2.9 times 10 to the negative 7th. So since our Kb value is larger, this is going to be a basic salt. So we already talked about if both of them cancel out, it's neutral. If the cation does not cancel and the anion does cancel, it's acidic. The opposite's true if your cation cancels and your anion does not, it's basic. If neither cancel, you need to compare your Ka and Kb values to figure out if it's acidic or basic. There's also other examples on page 730 of your textbook. So if you need additional help with this, check out figure 15.16. So like I said in class, there is also kind of a shortcut way to write these instead of writing the hydrolysis reactions for every single substance. So with our shortcut, we are going to look at our parent acid and our parent base. So simply looking at that cation, what base does it come from? The anion, what acid does it come from? So this is just kind of a shorthand way of doing it. But like I said, this is not going to be justification. So if it asks you to justify, you cannot do the shortcut. You must write those hydrolysis reactions. So correct justification will include the reactions of the ions in solution. So what we did during class. The shortcut, how you do it is simply split your compounds. So here we have ammonium chloride. So if we split this, we want to look at ammonium pairs up with what base. So ammonium comes from ammonia, NH3. The chlorine, what acid does it come from? So chloride comes from hydrochloric acid, the HCl. So here we have a weak base and a strong acid. So remember, strong acids or bases are going to cancel. So our anion will cancel, but our cation does not. Therefore, this is an acidic salt. So that's just kind of a quick way, if you're just simply looking at, is it acidic or basic? And you're not asked to justify. That's how you can figure that out. So kind of using this, we can then find the pH of different substances. So looking at the pH of the 0.1 molar NaOCl. So if we look at, excuse me. All right, sorry guys. So looking at what's the pH of NaOCl. So we need to split this salt to see if it should be acidic or basic. Excuse me. So sodium, its parent base is going to be NaOH, which is strong, so that will end up canceling out. OCl, its parent acid, is the HOCl. So that is weak. So this we're dealing with base overall. So we only need to write the hydrolysis reaction for our one that did not cancel. So for our anion, so writing this out for our anion is going to be OCl negative plus the water. And remember, it's weak acid, weak base. Ooh, that's a really long arrow. Let me erase that real fast. So that is going to produce, remember the OCl negative is going to steal a hydrogen from water. So it'll make the HOCl plus hydroxide. So we have 0.1 molar OCl negative because that's what we started out with. Remember, we ignore water because it's a liquid, and we didn't have any of our ions at the beginning. So we know that we're going to be adding our products and subtracting, sorry, my finger touched it, from our reactants. So our equilibrium amount should be 0.10 minus X. Our products will be X and X. Now, normally you would be given a Ka or Kb value. If not, you can simply look it up in your textbook. So I looked up in my textbook the Ka of HOCl, and it told me it was equal to 3.5 times 10 to the negative 8th. So a lot of times you might just have only Ka values. So remember, you can simply use those to find Kb. Since we are dealing with hydroxide and this is basic, we are going to need to find Kb at some point in time. So since we're solving with X, we need to plug into our Kb equation, but we don't have Kb, we have Ka. So remember, that's where you can solve for Kb by rearranging that Kw equation and dividing by Ka. So Kw divided by Ka, so 1.0 times 10 to the 14th divided by the 3.5 times 10 to the negative 8 gives us a Kb value of 2.9 times 10 to the negative 7th. So now that we know Kb, we can plug our equilibrium amounts into our Kb equation. So remember, Kb is still going to be equal to our products. So our products were the HOCl, which is going to be X, and the hydroxide, which is going to be X as well, divided by our OCl negative. Now we can ignore the X here because 0.10 is 1 times 10 to the negative first, whereas and our Kb value is to the negative 7th, so that's at least 3 different, so we can just do 0.10. So multiply by 0.1 to give you X squared. Take the square root to give you an X value equal to 1.7 times 10 to the negative 4th molar. Now this is the value of our OH. Ooh, sorry, my board's going crazy, y'all. So that's going to be the value of our hydroxide. So since we know hydroxide, we can find POH. So POH is going to be negative log of 1.7 times 10 to the negative 4th. So that's going to be 3.77. So if we're finding pH, remember we can subtract from 14. So we're going to have a pH of 10.23, which is basic, which we predicted. Let's look at the next one. So here we want to know what's the pH of 0.2 molar hydrozinium chloride, which is N2H5Cl, and it gives you the Kb value of hydrazine, which is the N2H4, which is 1.7 times 10 to the negative 6. So if we look at our salt, I'm going to write this off to the side, so N2H5Cl. If we split this down the middle, so we kind of have a clue that the hydrozinium chloride, the hydrozinium is going to become the hydrazine, the N2H4, whenever it loses a hydrogen. Whereas the chlorine has to absorb a hydrogen, that makes hydrochloric, which is strong, so it will cancel out. So we're only dealing with the acidic part. So we have the hydrozinium, the N2H5, which is a positive charge. It pairs up with water to produce the hydrazine, the N2H4, and H3O plus. So it does make the hydroniums, because we said this is acidic because our cation does not cancel. So looking at what we have, we know that we started with 0.20 molar hydrozinium. We did not have anything else at the beginning. And remember, we ignore water because it's a liquid. So we know we have to add to our product side, subtract from our reactant side. So that's 0.20 minus x, x, and x. Now, here's the thing. Because this is an acid, we need Ka, but it gave us Kb. So we can do the same thing we did on the previous problem. So Ka, if we rearrange that Kw formula, is Kw divided by Kb. So whenever we do the 1.0 times 10 to the negative 14th divided by 1.7 times 10 to the negative 6, we get that our Ka value is 5.9, times 10 to the negative 9th. Now, if we were to plug everything into Ka, so we have Ka 5.9 times 10 to the negative 9th is equal to our products, which is x times x, so you can simplify that to x squared if you would like, over the 0.20 minus x. Now, since the 0.20 would be 2 to the negative times 10 to the negative first, and our Ka is to the negative 9th, we can ignore that x value. A lot of times with weak acids and bases, you can ignore the x value. So we're simply going to put 0.20 on the bottom. So we need to multiply by 0.20 and then take the square root of both sides to find an x that is equal to 3.4 times 10 to the negative 5th molar. Now, this is equal to our hydronium concentration, which is equal to the hydrogen ion concentration. So to find pH, we simply need to do the pH is equal to the negative log of our H plus, or hydronium, which is 3.4 times 10 to the negative 5th. When we type that in, we get a pH equal to 4.46, which is acidic. All right, let's look at another example. This one's slightly different. Here it says, is 0.2 molar ammonium fluoride acidic, basic, or neutral? And it wants you to justify your answer. So remember, justify your answer, you need the full hydrolysis equation for each ion. So you cannot do the shorthand. So we do need to split this, but we need to write out our equations of ammonium and fluoride whenever they both react with water. So ammonium, remember, if that's acidic, it's giving up a hydrogen. So that will produce ammonia and hydronium. Now, ammonia is a weak acid, so that doesn't cancel out. We're okay there. But with the fluoride, since it's negative, it's going to attract the positive hydrogen from water to make hydrofluoric and hydroxide. Hydrofluoric is a weak acid. Ammonia is a weak base, not a weak acid. I misspoke. So neither of these are going to cancel. So we have to figure out, should it be acidic or neutral? So remember, when neither cancel, we need to look at our Ka and Kb values of our ions. So from our textbook, we can find Ka values. So we have the Ka of ammonium, but we need the Kb for the fluoride because that is our ion we're dealing with. So we can change this into Kb. I remember doing Kw, the 1.0 times 10 to the negative 14th, divided by Ka, 7.2 times 10 to the negative 4th. So we have a Kb value equal to 1.4 times 10 to the negative 11th. So whenever we compare Ka 5.6 times 10 to the negative 10th, to Kb, 1.4 times 10 to the negative 11th, our Ka value is larger, therefore this is acidic. So for a question like this, want to know if it's acidic, basic, or neutral, and it says justify, you want to make sure to write out your equations. If none of them cancel, you have to show your comparison of Ka to Kb to determine if it's acidic, basic, or neutral. All right, let's look at one more. Here, we want to know what's the pH of 0.0030 molar hydrocyanic acid. Now, this is a weak acid. So we do not have to do salt hydrolysis because it's already an acid or a base, whether it's weak or strong. So we remember that with weak acids, we have to do ice tables. So hydrocyanic, whenever it reacts in water, remember, will be a double reaction. Sorry, my board's going crazy again. So remember, the hydrogen, or the hydrocyanic acid, will give up a hydrogen to be cyanide and hydronium. So we are starting with 0.003 molar hydrocyanic. We're not starting with anything else at the beginning. And remember, we ignore water because it's a liquid. So we're going to be increasing on our product side by a factor of X, decreasing on our reactant side by a factor of X. So our equilibrium amounts are going to be 0.0030 minus X, X, and X. Now, the other information it did not give us is the Ka or Kb value. So if it doesn't give it to you, look it up in your textbook. In the back in Appendix 2, there's a whole table of Ka values. So Ka of HCN is equal to 6.2 times 10 to the negative 10th. So that's equal to our products, X squared, over our reactant, the 0.0030 minus X. Now that's to the negative third compared to the negative 10th, so they cancel. So we're going to multiply by 0.0030 and then take the square root to get an X value equal to 1.4 times 10 to the negative 6 molar, which remember is equal to our hydrogen concentration, our hydronium. So we can simply plug this into pH. So negative log of 1.4 times 10 to the negative 6. And our pH is going to be equal to 5.86, or 87, which is acidic.